So today I come to section 5.3, the fundamental theorems of calculus, part 2. The question in this session is, what happens if you integrate a derivative? And the fundamental theorems of calculus, in here I notate by FTC, gives the precise relationship between the derivative and integral. So Newton and Leibniz exploit this relationship and used it to develop calculus into systematic mathematics method. In particular, they saw that the fundamental theorem enabled them to compute area and integral very easily without having to compute them as limit of sum as we have been doing so far, right? So from now, we use this fundamental theorem. We don't have to use the limit of sum anymore. Okay. So fundamental theorem of calculus part 2, we say if f derivative of x is continuous on a and b, a to b, right? And then we have the integral from a to b of f derivative of x dx will be equal to fb minus f of a. Okay, so remember that. In this case, we are taking the antiderivative of a derivative, right? See that? So alternatively, if fx continues on a to b and fx, capital F, right, is antiderivative of f, then you're gonna just say the derivative of antiderivative of fx equal to I don't say the integral from a to b of fx will be the capital F of x minus capital F of a. So that is the way. Okay, so now second. Okay. So what's the main point from A? The differentiation and integration in some sense inverse process. See that? And what's the main point from part B? If f is continuous on A to B, we can compute exact net area under fx from A to B by finding an antiderivative for fx and evaluating fb minus f of a. Okay, so example 11. Find the net area under the parabola y equals to x squared from 0 to 1. Okay, so let's do example 11. You're gonna find the net area under the parabola y equal to x squared from the 0 to 1. So if you draw it, how it look like? Okay, so it's look like this. You guys know that it's going up like this, right? Y equal to x squared, right? And then from 0 to 1 is here. Okay, so the area under the curve is this guy. Okay, so now we have area A equal to 0, 1. So we are going to be from the integral from 0 to 1 of x squared dx, right? Okay, so by fundamental theorem, right? By fundamental theorem, fundamental theorem, FTC. Okay, plus. Okay, so I will have f of 1 minus f of 0. What is f of 1? The entire derivative of x squared, right? So we have equal to x cubed over 3 for both of these, and then we can write as 0 to 1, and then substitute 1 first. I have 1 cube over 3 minus 0 cube over 3. So you can see that the entire derivative of x squared f of 1 actually is this guy. See that? And the f of 0 in here is this guy. But I can also write in this form as x cubed over 3 from and from 0 to 1. Okay, so so now the answer will be equal to 1/3 as the answer, and I will just circle this answer. Okay. Let's do one more example. Example 12 here. We want to evaluate the 1 over x, evaluate of integral of 1 over x dx from 3 to 6. So make it bigger. Okay. Now, oh, that's big. Sometimes crazy, yeah. Yeah. Let me see. Okay, that's good. So I can use by fundamental theorem FTC with f of x equal to ln of x. So really, or we can just write at ln x only, because in here we are in the because we are consider at x from 3 to 6, so so x is on positive interval, so we don't have to worry about the negative sign anymore. So now I have integral from 3 to 6 of 1 over x dx can be equal to ln of 6. No, maybe I'm gonna write it first, so you guys can see the n of x from 3 to 6, and that's equal to area under 6 minus area under 3, and that's equal to area under 6 over 3 by the police of the natural log, and that's equal to area under 2. And if you use calculator, that's going to equal to 0.693 as the answer. So okay, so done with this one, and if we move to worksheet number 6 here, you can see that we have some exercise for you. There's 14, 15. Oh, wow, that's a lot. Anyway, let's stop this session here, and we'll see you at the class to do this. Okay.